Yeah, welcome everybody. We are opening this session with the first talk of Wen Chen, Philipp Spätig, and Hans-Peter Seiwert on mean stress effect on fatigue behavior of austenitic stainless steel in air and LWR conditions. And we are looking forward to your presentation, Mr. Chen.
Good morning, dear colleagues. My name is Wen Chen. I come from. Okay, yes, thank you. My name is Wen Chen. I come from the Powershell Institute in Switzerland. I'm also a PhD student in the Swiss Federal Institute of Technology in Lausanne. This is a bird view of our institute. It's quite beautiful. And in the coming 15 minutes, I will give you a short introduction about the mean stress effects on fatigue behavior of austenitic stainless steels in air and light water reactor environments. And my thesis director is Dr. Philipp Spätig, and also under the supervision of Hans-Peter Seiwert. My presentation is constructed in a background motivation and also a research approaches to introduction, and coming on the discussing about the mean stress effects on fatigue knife, the cyclic hardening, the fatigue cracking, and the correct correlation method of mean stress effect, and finally our short conclusions. As we all know, the pressurized water reactor and the boiling water reactor are the most common applied reactor type in the commercial usage. And the components like the pipes, the surgeon and the valves works in the high temperature water, mainly fabricated with austenitic stainless steel, and in the field experience, the fatigue is the main reason through the components integrate, and this vibration induces no stress or strain amplitude will induce a high cycle fatigue, and the temperature transient, the thermal stratification, the start and shutdown will induce the no cycle fatigue. The ASME design curve are most common applied method to evaluate the fatigue knife in the austenitic stainless steel. And a correction factor between the design curve and the mean curve has been introduced to try to introduce a conservatism between the fatigue knife design. However, in this diagram, we can see the red triangle, some red triangle drops at the left side of the design curve. That means the ASME design curve is not conservative enough to evaluate the fatigue knife austenitic steel works in the environment where the temperature, the strain rate, the strain amplitude meet the threshold concomitantly. And in the coming GSME design code and NRC design code, they take the temperature and dissolve the oxygen and the strain rate into consideration. However, we found that this is not enough, and the mean stress and the specimen geometry and the non-isothermal cyclic loading and the surface finish also has potential influence on the environmental assisted fatigue and not be sufficiently understood. And in this study, I will mainly focus on the mean stress and its cooperative effect with the environmental effects on the environmental assisted fatigue. In the research approaches, both experimental and modeling works are involved, and the fatigue test is mainly conducted in this kind of facility. It consists of a simulation, a light water reactors, environmental simulation loop, and also a fatigue test machine. This is a picture of this part, and this is a picture of the fatigue test part. This is normally the low temperature. Here is high temperature, and the materials applied materials is 316L austenitic stainless steel, and the standard cylindrical hollow specimen with a geometry of 2.5 millimeter, inner radius and a 5 mm outer radius was applied, and the specimen was heated from the inner side by the high temperature water, and the strain signal is measured by the extensometer attached on the specimen surface. And the sinusoid waveform with frequency 0.17 Hertz is applied, and normally most of the test is controlled under load control. And in this presentation, only the experimental fatigue test results will be presented. If you are interested in other parts like the materials characterization and the data analysis modeling, we can communicate after the presentation. And first, I will introduce the mean stress effects on the SN curves. Actually, the mean stress on the fatigue knife. By now, there are 66 tests has been performed in room temperature water, high temperature water, and high temperature air. Actually, it is quite an expensive test and quite time consuming. And the test is done, most of the test is done under load control with and without mean stress. And the mean stress of 0, 10 MPa, 50 MPa, minus 20 MPa, and minus 10 MPa has been applied. And from this diagram, this green star is the strain control test results. The squares are the load control test results. If we divide this diagram in two halves, the left is the no circle fatigue, the right is the high circle fatigue. In the left region, we found that both positive and negative mean stress has increased the fatigue knife. On the right high circle fatigue, we found that positive mean stress has decreased the fatigue knife and also the fatigue limit. On the other hand, the minus 20 MPa has increased the fatigue knife and fatigue limit. And on the other hand, we found the strain control test result correlate well with the load control test result, and the curve is fitted based on the Langer equation. And this is the test in the air condition. We found that it has a similar mean stress effect in the air condition, and except the 50 MPa mean stress in the high circle fatigue region is still not needed to be confirmed by the further test. And what is the behind mechanism of the mean stress effect? So maybe the direct answer is the cyclic hardening. If we take the test result example of with the stress amplitude 190 MPa in high temperature water, this is the strain amplitude corresponding to the loading circle. We found that the test with mean stress has undergone two phases of hardening phase. The first hardening and the second hardening. Especially the test with minus 20 MPa has most pronounced hardening, second hardening. The second hardening is the result in smaller strain amplitude, which is a tentative reason for the increase of fatigue knife. And this is also example of with stress amplitude of 190 MPa in air. It is also has similar strain evolution in the air condition. So we want to have a more in-depth understanding about the mechanism of the mean stress effect, about the second hardening. So we cut the specimen after test specimen to check in the TEM, in the EBST, and in ECI. And I take an example picture. This specimen is tested after with stress amplitude of 210 MPa or mean stress of minus 20 MPa in high temperature water. And many planary dislocation structures were developed, and the coordinate structures were exclusively found in the second hardening phase. This kind of structure may be responsible for the second hardening. If we plot the average strain amplitude corresponding to the stress amplitude, we found that there is a linear correlation between these two parameters. And if we take a look at the slope of different mean stress condition, we found that the slope of the with mean stress has a smaller slope than the without mean stress, which means the mean stress has hardened materials. If we compare the slope in two different environments. We found that the slope with 0 mean stress and the slope with minus 20 mean stress is almost similar in two different environments, but the slope of 50 MPa mean stress in high temperature water is bigger than the one in the air condition, which is contradicted to the hardening and fatigue increase effect of cyclic hardening. And then we studied the mean stress effects on the fatigue crack initiation and crack growth. We take the fracture surface into the fractographic investigation. This kind of dark area is because of corrosion in high temperature water, which can represent the fracture cracking zone. And the dark area, we found that the cracks initiate only from the inner surface at multiple points, except the one with the minus 20 MPa. Only one initiation point was found. And the dark area of the right three pictures is smaller than the one on the left, which means the 10 MPa, 50 MPa, and minus 20 MPa has the strain effect of the crack formation. And normally, as we all know, the positive mean stress will induce some more strain localization and rotating strain. And this is reflected by the after-tested specimen's wall cross-section, which has a bigger crack openness and more prolonged snaking effect. And also, this picture can also prove that the minus 20 MPa has strong crack, the strain effect on the crack initiation. There is low crack on the wall cross-section. And in order to check the mean stress on the crack initiation and the growth effect on the crack growth, we measure the spacing situation along the main crack of the fracture surface, and we found the mean stress. These two curves is with positive 50 mean stress, minus 20 MPa mean stress. The mean stress has retarded the crack growth rate, the crack growth. And with the measured crack growth circles, we can calculate the physical crack initiation circle. This is crack growth circle. This brown is the crack initiation circle. Orange is crack initiation circle. We compare the circle of two different stages with different mean stress. We found that the mean stress, both positive and negative mean stress, has increased the fatigue, both life circle in both stages. And also similar phenomena also found in the high temperature air condition. After we have a phenomenal understanding about the mean stress effect on the fatigue knife, on the cyclic hardening, and on the crack initiation and crack growth, we want to correlate the mean stress and try to predict the fatigue knife. We applied the conventional mean stress correction model, like the Goldman model, Gabor model, and we found it can fail to correlate our tested fatigue knife with mean stress. So we have modified the SWT model parameters, which coupled with the maximum stress and the average strain. And from these two diagrams on the two different environments, here's in the high temperature water, here's in the high temperature air, we found this modified SWT parameter correlates the fatigue knife data with mean stress and with different control model well correlated. So finally, we go to our short conclusions regarding the mean stress effects and the net water reactor environmental effects and the test results correlation. We found a non-zero mean stress induced the cyclic hardening of the material and result in increase of fatigue knife. And the minus 20 MPa mean stress restrains crack formation, and the non-zero mean stress retards crack initiation and crack growth. In the net water reactor environment, the cracks initiate only from the inner surface in test in net water environment. However, either minor cracks initiating from outer surface in air condition. In high temperature water, most of the reduction in fatigue knife is accounted for in the physical cognition stage. And the modified stability parameter correlates well the fatigue knife gained under the different mean stress and the control mode. Thank you.